Alright, so let's see. I have my Mako here, once again. This time, rather than caring about how far it takes to stop, what I care about is how much force he's applying with his tail. I had to make up some of these numbers. I looked at some papers and stuff, and I just got myself more confused. There was actually a reasonably interesting paper about it. It's just that getting from here to there is getting from what they had in that problem to this number, which I think is about the order of 10 too high, is a little complicated because they cared about the underlying physics a lot more. So rather than caring about the forces and the basic concepts, they cared about the particular effects of the model, right, that they were using. So I had to try to figure out from that model what was actually going on, and I was not really successful. So I just guessed. I got pretty close, and then I guessed, and then I arranged it a little bit so that it would be a nicer number. I say that, but it doesn't end up being a nice number. We'll find that out. So what we want to do is we want to figure out, how fast the shark, if the shark is going at a speed v, if the shark is going at 50 kilometers per hour, and he's getting pulled back by the water, right? The water wants him to stop. So if he stops swimming, he'll drift to a stop, right? Just sort of like what we showed in the last video. So if that's going to happen, then, he has to have some other force from his tail fin this way. We want to figure out how much force that Mako has in his tail fin. Okay, so I think that's a pretty reasonable sort of thing to want to know, right? So how would we do that? We do this the way we normally do Newton's laws, which is draw a bunch of forces. So we'll bring out the free body diagram, which is everybody's favorite. And we'll say, okay, well, if I have a shark, what sort of things go on with my shark, right? If I have my shark, this one's even worse than the last shark. Oops. Okay, so if I have my shark, again, we'll say sharks have weight. I still ran into the edge. Also has buoyancy keeping it up, right? They don't sink to the bottom very easily. Let's see, what else does it have? Well, we just said there was a drag force coming this way, and a forcey force coming that way. So our fin force, F, is going forward, and our drag is going backwards. That's actually the meat of the problem. And then we have the opposite direction, which we're ignoring, which is just sharks sitting in the water not doing anything. So, we'll just assume that the shark is having a nice time at a nice level depth. And then there's no net force. So I'll draw that 0 with an arrow through it. The arrow just indicates the direction. The 0 indicates no net force. All right, so there's the physics. Now we have to turn that into math. Well, how do you do that? Well, when you have one of these free body diagrams, right, you just say everything along this axis, F minus D, is equal to whatever the net force is in that direction. In this case, it's 0. And then, okay, so that's the y direction. And then over here for the z direction, we'd have everything in the z direction, right? B minus W. B is going up, W is going down, and that's equal to 0. Only we don't care about this part, right? Those two things just cancel and there's no action. And we care about the action because this is an action class. So now that we have that, we want to substitute the drag. Now, what kind of drag is this? It's turbulent drag. That means it's quadratic drag. So that means we substitute in, we don't want an equal sign, we want a minus, the formula for quadratic drag, which is another constant times v squared. That's why it's quadratic drag. And that's equal to 0. Well, that means If we add this term to both sides, we can cancel it out here and put it over there. Right? If something minus something else is equal to 0, that means that something is equal to that other something. F is equal to C2 V squared. So this is what we need to find. And we have the drag constant there, and we have the speed there. Looks like we don't need that mass. So the Mako got on the scale for no particular reason. So probably felt bad about itself a little bit because, that's what scales are for. So here we are. We want to use this equation. There it is again. So how do we use that equation? Well, we just have the numbers, so we plug the numbers in. Right? So we've got the force is equal to the 15 kilograms per meter, which is great, times the square of the 50 kilometers per hour. Once again, turns out, though, this is squared. We still have to get rid of the hours and turn them into seconds, right? So how do we do that? Let's see. I said that for every hour that we had 3,600 seconds. So we'll keep up with that one. And how do we convert kilometers to meters? Right? If I have 1 kilometer, I want to get rid of the kilometer in the numerator. I'm going to have to square that. So I have to put the kilometers in the denominator. And I need to have a meter up here. How many meters do I have in every kilometer? Last time I checked it was 1,000. So we'll use 1,000. Okay, so now we have to go through the whole entire process. So fortunately these things are squared, so that 3,600 becomes a 36 and that 1,000 becomes a 10. So now we have 15 times 50 squared times 100 divided by 36 squared. And I'm not even going to pretend to try to do that one. So that'll be 2894 if I calculate it in a calculator, or if I plug it into a calculator. So 2894 newtons. 2893.5 I think is what I got, last night or the night before when I did that. And so there we are, we have the 2894. So what did we do? First, we looked at the physics by drawing a free body diagram. We said, okay, what sort of things are going on with this shark, right? He's a heavy shark, so he's getting pulled down this way. He's a buoyant shark, so he doesn't fall to the bottom of the ocean until he dies. I don't know exactly how that works. He's going at a speed in this direction, so even though he has a drag pulling him back, his tail fin is pushing him forward, propelling him forward with that force F. And like we said, that propulsion, since it's coming from an internal source, coming from his muscles, has to be mediated through a drag force or a frictional force. Possibly you could use another force, but I don't know of any others. All the others seem to do things stay inside or come from outside. All right, so that's how we build up that free body diagram. So the free body diagram is a way to look at this. This has zero net force. It has zero net force because the speed is constant. Okay, so that lets us get the relevant equations that we can use to solve this. So we just took everything in that y direction, the f minus d, and converted it into a nice simple equation, which is the thing we want, that f is equal to some function of the two things we know. So we know the C2 and we know the V, so we just have to plug numbers in, can do a couple of conversions to get into the right units, and we end up with a nice, pretty answer that shows up on your screen right now, 2894 newtons. All right, so I hope that was simple enough. If you have any questions, I've turned off the comments. So, get in touch with me via email or something. Actually, I didn't. Did I even turn off the comments here? I think this is going to be unlisted, right? So I'm not sure if I even have comments on unlisted. Anyways, I'll turn off the comments anyway, just in case. Yeah, just email me for questions, or if I'm getting a lot of questions, I'll start setting up chat times and stuff like that. That's probably not so great. It'll probably take me half an hour to upload this video. This is how good my internet is at home. So I might not be doing a lot of chats. All right. So thanks for listening. I hope you enjoyed hearing about Makos and having tail fins and stuff like that. I'm sure a lot of you do have tail fins. I think looking at my channel analytics, most of the people who watch these things actually live in the middle of the ocean. So most of the people who live in the middle of the ocean tend to be fish. So I will see you next time. Bye now. Yeah, I'll leave now before I make more bad jokes. Bye now.